Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Dielectric Properties 8 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. First we will see the derivation of Harbilic-Nigami equation for dielectric relaxation, detailed study of molecular relaxation time, and then you will learn about Harbilic and Nigami dispersion and also Froelich analysis. Harbilic-Nigami equation for dielectric relaxation. The relaxation time is a function of temperature according to a chemical process defined by tau is equal to tau 0 exponential over b by kt, in which tau 0 and b are constants. It is called the Arrhenius equation also. There is no theoretical basis for dependence of chi on T, and in some liquids such as those studied by Davidson and Cole in 1951, the relaxation time is expressed as tau equals to tau 0 into exponential of A by K into T minus Tc, where Tc is a characteristic temperature for a particular liquid. At T is equal to Tc, the relaxation time is infinity according to equation 2, which must be interpreted as meaning that the relaxation process becomes infinitely slow as we approach the characteristic temperature. The observed correspondence of temperature T with viscosity is qualitatively in agreement with the molecular relaxation theory of Debye, who obtained the equation tau m is equal to 3 eta v divided by k into T, where tau m is called the molecular relaxation time, eta the viscosity, v the molecular volume, which is 4 by 3 pi a cube, where a is the molecular radius, assumed spherical. The molecular volume required to obtain agreement with the relaxation times is too small for glycerol and propylene glycol, which is 10 to the power minus 31 meter cube, and of reasonable size for N-propanol, which is 60 to 900 into 10 to the power minus 30 meter cube. The spread in these values arises due to the fact that the molecular relaxation time tau d and the relaxation time tau obtained from the dielectric studies may be related in several ways. The inference is that for the first two liquids, the units involved are much smaller, whereas for the third named liquid, the unit involved may be the entire molecule. These details are included here to demonstrate the method employed to obtain insight into the relaxation mechanism from measurements of dielectric properties. Molecular relaxation time. Molecular relaxation time may be expressed in terms of the viscosity of the liquid and the temperature as tau is equal to 4 pi eta a cube by k into T, where a is the molecular radius. The molecular relaxation time is assumed to be due to the inner friction of the medium that hinders the rotation of polar molecules. However, tau m is a function of viscosity. As an example of applicability of equation 4, we consider water that has a viscosity of 0.01 pours at room temperature and an effective molecular radius of 2.2 into 10 meter, leading to a relaxation time of 2.5 into 10 to the power minus 11 second. At relaxation, the condition omega tau is equal to 1 is satisfied, and therefore omega is equal to 4 into 10 to the power 10 per second, which is in reasonable argument with relaxation time obtained from dielectric studies. Equation 4 is however expected to be valid only approximately because the internal friction hindering the rotation of the molecule, which is a molecular parameter, is equated to the viscosity, which is a macroscopic parameter. It is well known that the viscosity of a liquid varies with the temperature according to an empirical law. Eta is proportional to exponential of C over kT, in which C is a constant for a given liquid. Therefore, equation 4 may now be expressed as tau m is proportional to 1 by tau into exponential of C by kT. The relaxation time increases with decreasing temperature, as found in many substances. Froelich analysis. To understand Froelich's model, let us take the electric field along the plus axis or positive axis and suppose that the dipole can orient in only two directions, one parallel to the electric field, other anti-parallel. Let us also assume that the dipole is rigidly attached to a molecule. The energy of dipole is plus W when it is parallel to the field, and it is minus W when it is anti-parallel, and 0 when it is in the perpendicular direction. As the field alternates, the dipole rotates from a parallel to the anti-parallel position or vice versa. Only two positions are allowed. A rotation through 180 degree is considered as a jump. Froelich generalized the model, which is based on the concept that the activation energies of dipoles vary between two constant values W1 and W2. Froelich assumed that each process obeyed the Arrhenius relationship and relaxation times corresponding to W1 and W2 are given by tau 1 is equal to tau 0 into exponential of W1 by kT and tau 2 is equal to tau 0 into exponential of W2 by kT. The dipoles are distributed uniformly in the energy interval dW and make a contribution to the dielectric constant according to JW or HW. The analysis leads to fairly lengthy expressions in terms of the difference in the activation energy W2 minus W1, and the final equations are JW is equal to epsilon minus epsilon infinity divided by epsilon s minus epsilon infinity, which is equal to 1 minus 1 by 2s ln of 1 plus x square e to the power s divided by 1 plus x square e to the power minus s. Similarly, HW is equal to epsilon divided by epsilon s minus epsilon infinity, which is equal to 1 by s into exponential e to the power s by 2 tan inverse of x minus exponential of e to the power minus s by 2 tan inverse of x, where s is equal to W2 minus W1 by kT and x is equal to omega p by omega. Here omega p is the frequency at which epsilon double prime is maximum. Since s is a function of temperature, the shape of JW and HW curves will vary with temperature, tending towards a single relaxation time at higher temperature. Omega p is related to tau 1 and tau 2, and omega p is equal to 1 by tau 1 into exponential of minus W2 minus W1 by kT, which is equal to 1 by root over of tau 1 into tau 2. Figure 1 shows the factor epsilon double prime divided by epsilon double prime max as a function of omega by omega p calculated according to epsilon double prime divided by epsilon double prime max is equal to tau root over of tau 2 by tau 1 into tan inverse of omega by omega p root over of tau 1 by tau 2 into tan inverse of omega by omega t whole divided by tan inverse of tau root over of tau 2 divided by tau 1 minus tan inverse of root over of tau 1 divided by tau 2. Figure 1 shows the dependence of dielectric loss epsilon double prime omega according to equation 8 for three values of the parameters tau 2 square root of tau 2 divided by tau 1 is equal to 1, 5, 10. The temperature dependence of epsilon double prime max in the context of Froelich theory is often explained by assuming asymmetry in the energy level of the two positions of the dipole. At lower temperatures, the lower well is occupied and the higher well remains empty. The number of dipoles jumping from the lower to higher well is 0. However, with increasing temperature, the number of dipoles in the higher well increases until both wells are occupied equally at Kt is very greater than W2 minus W1. Therefore, there will be a temperature range depending upon the energy difference in which S double prime increases strongly. According to this model, the loss factor is epsilon double prime is proportional to 1 by 3 Kt cos hyperbolic square of W2 minus W1 divided by 2 Kt, which is a function of T, where W2 minus W1 is the difference in the asymmetry of the two positions. Plot of Ft versus T for various values of V are shown in the range of V is equal to 0 to 100 MeV in figure 2. By comparing the observed variation of epsilon double prime versus T, it is possible to estimate the average energy of asymmetry between the two wells. This is the figure 2 and which shows the temperature dependence of the relaxation strength calculated for various values of the asymmetry potential W2 minus W1. So here you can see that above 20 MeV, so it saturates and then goes down, whereas for V is equal to 0 MeV, it continuously decreases, and at 350 Kelvin it almost merges to that of 20 MeV curve. Havrelik and Negami dispersion. Havrelik and Negami dispersion is given to the more complicated structure, in particular polymer materials. The complex plane plots of polymers obtained by isothermal measurements do not lend themselves to the simple treatment that is used in case of simple molecules. The main reasons for this difficulty are the dispersion in polymers is generally very broad, so that data from a fixed temperature are not sufficient for analysis of the dispersion. Data from several temperatures have to be pooled to describe dispersion meaningfully. The shapes of the plots in the complex plane are rarely as simple as that obtained with molecules or simpler structure, rendering the determination of dispersion parameters very uncertain. In an attempt to study the alpha dispersion in many polymers, Havrelik and Negami have measured the dielectric properties of several parameters. Alpha dispersion in a polymer is the process associated with the glass transition temperatures, where many physical properties change in a significant way. In several polymers, the complex plane plot is linear at high frequencies and a circular arc at low frequencies. Attempts to fit a circular arc coal is successful at lower frequencies but not at higher frequencies. Likewise, an attempted fit with a skewed circular arc Davidson-Colle is successful at higher frequencies but not at lower frequencies. The two dispersion equations reproduced here for convenience are represented by epsilon star minus epsilon infinity divided by epsilon s minus epsilon infinity, which is equal to 1 by 1 plus g omega tau to the power 1 minus alpha circular arc coal, and epsilon star minus epsilon infinity divided by epsilon s minus epsilon infinity equals to 1 by 1 plus g omega tau 0 to the power beta skewed semicircle, which is Davidson-Colle. Combining the two equations, Havrelik and Negami proposed a function for the complex dielectric constant as epsilon prime minus epsilon infinity divided by epsilon s minus epsilon infinity is equal to 1 by 1 plus g omega tau h minus n to the power 1 minus alpha whole power beta. When beta is equal to 1, the circular arc shown above is generated. When alpha is equal to 0, the skewed semicircle is obtained. When alpha is equal to 0, and beta is equal to 1, the derived function is obtained. For convenience, we omit the subscript hn hereafter. To test the relaxation function given by equation 9, we apply successively the de Moivre's theorem and rationalize the denominator to obtain the expressions. Epsilon prime minus epsilon infinity is equal to 1 by r to the power beta by 2 epsilon s minus epsilon infinity cos of beta theta, and epsilon double prime is equal to epsilon s minus epsilon infinity sine of beta theta, where r is equal to 1 plus omega tau to the power 1 minus alpha sine alpha pi by 2 whole square plus omega tau to the power 1 minus alpha cos of alpha pi by 2 whole square, and theta is equal to tan inverse of omega tau 2 minus alpha to the power 2 minus alpha cos of alpha pi divided by 2 whole divided by 1 plus omega tau 1 minus alpha sin alpha pi by 2. Equation 9 may be examined for extreme values of omega, namely omega tends to infinity and omega tends to 0. For the first use, that is omega tends to infinity, as equation 9 becomes epsilon star minus epsilon infinity divided by epsilon s minus epsilon infinity is equal to j omega tau to the power beta into alpha minus 1, which is equal to omega tau to the power beta into alpha minus 1 cos of beta alpha minus 1 pi by 2 minus j sine of beta into alpha minus 1 pi by 2, and tan of beta alpha minus 1 pi by 2 is equal to epsilon double prime omega which tends to infinity divided by epsilon prime omega tends to infinity minus epsilon infinity. At very high frequencies, epsilon double prime is proportional to epsilon prime minus epsilon infinity, which is proportional to omega to the power beta into 1 minus alpha. For the second case, as omega tends to 0, epsilon star minus epsilon infinity divided by epsilon s minus epsilon infinity is equal to 1 minus beta into j omega tau to the power alpha minus 1, which is equal to 1 minus beta into omega tau to the power beta into alpha minus 1 cos of beta alpha minus 1 pi by 2 minus j sin beta into alpha minus 1 pi by 2, and tan alpha pi by 2 is equal to epsilon omega double prime and omega tends to 0 and epsilon s minus epsilon prime as omega tends to 0. From equations 10 and 11, we note the following with regard to the dispersion parameter. A. As omega tau tends to infinity, epsilon prime tends to epsilon infinity and epsilon double prime tends to 0. Therefore, epsilon star is equal to epsilon infinity. As omega tau tends to 0, epsilon prime tends to epsilon s and epsilon double prime tends to 0. Therefore, epsilon star is equal to epsilon s. We can therefore evaluate epsilon s and epsilon infinity from the intercept of the curve with the real axis. To find the parameters alpha and beta, we note that equations 10 and 11 result in the expression epsilon double prime divided by epsilon prime minus epsilon infinity is equal to tan beta theta, which is equal to tan alpha, tan phi. By applying the condition omega tau tends to infinity to equation 13 and denoting the corresponding value of phi as phi L, see figure 3, we get phi L is equal to beta into 1 minus alpha pi by 2, which provides a relation between the graphical parameter phi L and the dispersion parameters alpha and beta. Again, the relaxation time is given by the definition omega tau is equal to 1, and let us denote all parameters at this frequency by the subscript p. Havriliak and Negami also prove that the bisector of angle phi L intersects the complex plane plot at epsilon p star. The point of intersection yields the value of alpha by 1 by phi L log of epsilon p star minus epsilon infinity divided by epsilon s minus epsilon infinity, which is equal to minus of 1 by pi into 1 minus alpha into log of 2 plus 2 sin alpha pi by 2. The analysis of experimental data to evaluate the dispersion parameters is carried out by the following procedure from the complex plane plots. The low frequency measurements are extrapolated to intersect the real axis from which epsilon s is obtained. The high frequency measurements are extrapolated to intersect the real axis from which epsilon infinity is obtained. If data on refractive index is available, then the relation epsilon infinity is equal to n square may be employed in specific materials. The parameter phi L is measured using the measurements at high frequencies. The angle phi L is bisected and extended to intersect the measured curve. From the intersection point, the frequency is determined and the corresponding relaxation time is calculated according to omega is equal to 1 by tau. The parameters epsilon p prime minus epsilon infinity and epsilon double prime are also determined. So figure 3 shows the complex plane plot of epsilon star according to Hn function. At high frequencies, the plot is linear. At low frequency, the plot is circular. The Havrelik-Negami function is found to be very useful to describe the relaxation in amorphous polymers which exhibit asymmetrical shape near the glass transition temperature Tg. In the vicinity of Tg, the epsilon double prime versus log omega curves become broader as T is lowered. It has been suggested that alpha parameter represents a quantity that denotes chain connectivity and beta is related to the total density fluctuations. Chain connectivity in polymers should decrease as the temperature is lowered. The A parameter or the alpha parameter slowly increases above Tg, which may be considered as indicative of this. So students, let us summarize what we have learned in this module. In this chapter, derivation of Havrelik-Negami equation for dielectric relaxation was done and a detailed study of molecular relaxation time was carried out. We have also learned about Havrelik and Negami dispersion and also Frohlich's analysis. Thank you.